Okay, equilibrium constant expression. So I need you to really differentiate between this and the rate expression because they look similar and they are not. So make sure that you are keeping in mind what the rate expression looks like versus the equilibrium constant expression. And so let me give you a generic equation, and we will write out an equilibrium constant expression for it. So 2a plus b produces C plus 3D. We'll use that as our generic. And so in the equilibrium constant expression, which the variable is Kc, this is going to be equal to C d to the cubed over a squared times b. Okay, that's going to be our expression here for the equilibrium constant expression. So a couple of things to make note of. Number one, or differentiate. In the kinetic expression, the superscripts have to be determined experimentally. In the equilibrium expression, the superscripts are the coefficients. They are the coefficients in the balanced equation. So that is one of the biggest differences right there, is that the superscripts are the coefficients. So the coefficient of the product D is 3. We're going to make 3D. That is the coefficient. It does not have to be determined experimentally. And then the concentrations are the same. It's the concentration of C, just like it was in the kinetics equation. One thing also here you notice in the kinetic expression, we only dealt with reactants. In the equilibrium expression, where we're concerned with how much product versus how much reactant, both sides of the equation are in the expression. The product side is always on the top, and the reactant side is always in the bottom. And so this is how you would do a equilibrium expression. The concentrations superscripted to the coefficients with the products on the top and the reactants on the bottom of our expression. So let's do a couple of examples. All right, so here is a reaction. This is the contact process. Sulfur dioxide plus oxygen making sulfur trioxide. That sulfur trioxide is then bubbled through water to make sulfuric acid. It's a large-scale industrial process. We'll learn more about this later this unit as well. This is not balanced, so we need to balance this in order to do the equilibrium expression. We're going to put a 2 here, and we're going to put a 2 here. That should balance it. 2 sulfurs, 4, 6 oxygens. So that's good. Now let's draw or write the equilibrium expression for this. So it's the products over the reactants. The product is going to be the concentration of sulfur trioxide raised to the second power, because we have a 2 coefficient there, divided by the concentrations of the reactants, so sulfur dioxide to the second power and oxygen to the first power. And so there is your equilibrium expression for that particular reaction. Let's do another one. Another one that we will be looking at as an industrial process is the conversion of nitrogen and hydrogen into ammonia. So nitrogen gas plus hydrogen gas producing ammonia gas. And again, so if we're going to do the equilibrium expression, we need to balance this reaction. And so we're going to put a 2 on the ammonia, a 3 on the hydrogen, and that should take care of it. And so to write our expression here, we're going to have the concentration of ammonia to the second power over the concentration of nitrogen to the first and the concentration of hydrogen to the third. So there would be our equilibrium expression for that particular process. So writing equilibrium expressions is really not that difficult. It's pretty basic. Just make sure that you differentiate it between a kinetic expression. It's kind of after a while, and we're doing both of them. You get to a test, particularly the IB exam. they start asking about equilibrium, and you write a kinetic expression. Or they ask you about a kinetic expression, you write an equilibrium expression. So just make sure you don't confuse those two, because they do look similar in a lot of aspects. Now, let's talk about the value of Kc and what the value of Kc tells us. That's supposed to be the word of there. Value of Kc. Okay, so let's take a look at a really, really simple generic reaction. Reactant A converts to product B, and the coefficients for both of these are 1s, and so the equilibrium expression is going to be Kc equals the concentration of B over the concentration of A. Okay, so initially we start out with all A, and let's say that our concentration of A is 1 molar. And we start with 0 B, and so that is 0 molar. And at equilibrium, let's say that half of A converted into B. So at equilibrium, if half of A converted into B, where there'd be half of A left, 1 molar divided by 2 is half, and we would have 0.5 molars of B, because for every 1 A that decomposes or reacts, we make 1 B. So at equilibrium, we would have 0.5 and 0.5. If we plugged it into the Kc value at equilibrium, we'd get a Kc value of 1. And so what does an equilibrium expression value of 1 tell you? An equilibrium expression value of 1 tells you the reaction proceeds to the midpoint. Half of the reactants convert to the products. Getting a Kc value of 1 is highly unlikely. It just doesn't happen very often. But that's what it tells you. Now, let's say that we took this same reaction, and instead of having half of A convert into B, and we start with 1 molar still, 0 molar of B to begin with. Let's say that just a very small portion of A converted into B, so only 0.1 molar or 0.1 moles converted. That would leave us 0.9 left, and we would produce, we would add 0.1 over here, so we would have 0.1 molar of B. So just a little bit of A converts into B. If we plug that into our equilibrium expression, we'd have 0.1 over 0.9, okay, and that would be a value of 1/9. That would be 0.11. And so if we have a Kc value less than 1, then what that tells you, what is favored, which side of this reaction is the favored side of the reaction? Well, it's favored here to have A, so that tells you that the reactants are favored. The reactants are the favored side of the chemical reaction. At equilibrium, once equilibrium is established, there are more reactants than products. So the Kc value is less than 1. So logic tells us then that if the Kc value is greater than 1, then the product side is favored. And we can look at that as well. So if we erase these numbers up here, and if instead of just a little bit of A being converted, a lot of A was converted, so 0.9 moles of A was converted, there would only be 0.1 left, and we would make 0.9 over here because it's a 1-to-1 ratio. So we'd have 0.9 there. We'd have 0.9 over 0.1, that would be equal to 9. And so a value of Kc larger than 1, products are favored. These three little facts here are quite important in understanding equilibrium. And so commit those to memory. Kc values less than 1 favor the reactants. Equilibrium expression values greater than 1 favor the products. The larger the value, if it's much larger than 1, then the products are highly favored. If it's much less than 1, then the reactants are highly favored. So we can even differentiate between slightly favored versus highly favored in the chemical reaction. What is favored or not favored? Now I want to bring in the catalyst here as well. How does a catalyst affect the equilibrium expression, the value of the equilibrium expression, the Kc? How do catalysts affect this? Now this is a trick question, honestly. IB will ask it though, so I want to make sure you understand what's going on here. So a lot of people are going to say, hey, catalyst is going to make it go to the right, and therefore the Kc value is going to increase because we're going to have more products. But remember, what does a catalyst do? A catalyst speeds up the rate of a reaction. It does not shift where equilibrium lies. And so if you look at your enthalpy level diagrams with and without a catalyst, what a catalyst does is a catalyst lowers that activation energy. That increases the rate of the forward reaction, but it also increases the rate of the reverse reaction. And so the reverse reaction happens faster, the forward reaction happens faster. What a catalyst does not do is it does not influence equilibrium. It does not influence equilibrium. What it does is it allows equilibrium to be reached faster. It allows equilibrium to be reached faster, but it does not affect the value of the equilibrium expression. So make sure that when you are asked that question, I'm going to ask you that question on quiz or test, how does a catalyst affect the value of Kc? It does not affect the value of Kc. A catalyst does not influence the equilibrium expression. It simply allows the equilibrium to be reached faster or sooner. And that is an important thing. It is important to reach that equilibrium faster, especially in an industrial process. We want to produce our products as fast as possible. And so it is important. It just doesn't alter the value of Kc. It doesn't alter how much you produce. It alters how much you produce in a given period of time, but not how much you produce overall. Okay? So understand how a catalyst affects Kc, understand how to write equilibrium expressions, understand how the given value of Kc, what the value of Kc tells you about whether the products or the reactants are favored in the reaction.